Bless you.
So like I said, I literally want you to write maybe off to the side of each graph. The maximum is this. The minimum is that. What you think that would be. Take about another minute here to get everything as clear as we can, and then we'll pair. Okay, why don't you pair up with a partner there at your table, or maybe a couple of partners, share, or let's compare, and we'll share out after this, okay? Tell each other what you got.
Megan, what'd you get? Do we? Okay, so I was thinking.
All right, let's share. Let's try to get as many tables involved as possible. So on any graph, you just say, I think the maximum on the lower right one is whatever. You just share what you're feeling confident about. Merrick, what do you think?
Maximum on the upper left one is 4.
Okay, so the max, we're talking about the upper left, max 4. Okay, since we started off with the upper left one, let's keep going with the upper left one. Did anybody find a minimum for the upper left graph? What'd you find?
-2.
Okay, so let's focus on that for the moment. How do the rest of you feel about those responses? Correct, incorrect, halfway right? Luke?
Well, is it going to be a maximum if it's a sharp point?
Is it going to be a maximum if it's a sharp point? What do you think about that? Anybody? It's a point.
So it is, like, even if it's the highest point, it doesn't matter. It's like a sharp point.
Well said. I think that's really well said. Max and min is simply talking about, kind of like what Carter said, is it the highest? If the answer is yes, we really don't care if it's a sharp point, a rounded point, or any other variety of point. We're just looking for the highest point in whatever shape it takes. Great question, for sure. Anybody else? So is your silence saying that you agree with these two, that for the upper left, that's that's the case? Anna?
I just have a question, like, do they have to be coordinate points? Like,
Great question. So are you thinking like 0, 4 and -3, -2?
yeah.
Yeah. So usually if I ask for what's the maximum value, I'm asking what the maximum y value is. There might be times when I might say, give the x coordinate for the relative minimum, and there you just give the x. If it just says find the max, just give the y value that corresponds with the max. Yeah, good question. And a lot of times the x coordinates will like play into that. Like you will have used them to get to your answer, but that's kind of what I'm talking about. This is well done. I agree completely with these guys on upper left. Max 4, min -2. Because it's the high point and it's the low point. It really is just that simple. Okay, so what about the other 3 graphs? Who wants to take one of those on? Minimum, maximum. What'd you come up with? Nothing, huh? No? Okay, what do you think is the... So upper left is a pretty straightforward one, right? Because it doesn't have any of those open circles. Which one also doesn't have any open circles? Let's talk about that one. Can anybody mention max and min on that one? Because the open circles complicate things. I'll give you that. But lower right doesn't have that. What do you think, Tyler?
So the max was 4, and the minimum was -3.5.
Okay, so max 4, min -3.5. Okay. What do you guys think? Is the high point at a y value of 4? And is the low point at -3.5? Pretty much looks like it to me. Yeah, I think that makes a lot of sense. I would put a blue, why did it do that? What was this? Max. I was trying to get fancy and my computer didn't like it. Here we go. And you said max 4, min -3.5. I think that looks great. I really do. Is anybody brave enough to take on the other 2? Come on. Swing and miss. Swing and hit a home run, fall flat on your face, or be the champion. I don't know, whatever. Just try. Merrick.
Bottom left, the minimum is the limit as x approaches 3.5.
And let's give it a name. Let's say that it's f of x.
Nice.
Okay. Y'all understand what Merrick is saying? As x approaches 3.5, min. What about a max? Anyone can answer. Oh, so disappointed. Love to hear your contributions. Did anybody think the max was similar, like sort of a limit idea? Oh, are you going to make me just tell you?
The limit as x approaches 4.
Okay. No? Yes?
Yeah.
4.5-ish? Okay. I don't know if ish is an official math word, but I'm going to put it up there. We're going to talk about ish right now. So take a look at this one for a second. So the open circle means that the function is not defined right there, right? So limit as x approaches 3.5. We can clearly see, at least from the graph, it looks like the limit does exist. Does it not? The limit clearly exists because the behavior from the left and the right certainly appears to be the same. So I think we could say the limit exists. My question to you comes from here. How close can I get to 3.5? How close can I get? Say again?
Like 3.49 repeating.
How many nines?
Like 9, like infinitely.
Well, we don't live in the We don't live in the infinity, unfortunately. That'd be kind of cool. So there has to be, like when I say, how close can you get? There has to, you got to tell me a number, right? 300 nines. Okay, so 3.4 with 300 nines. Well, couldn't Gavin top that? What could you do?
301.
Oh, 301 nines after the 3.4, correct? Well, couldn't Anna do better than that?
Yeah,
How many could you do?
I can do 10,000.
10,000. She blew you guys out of the water. It's like, she's killing you. I bet you somebody from Shirley's table could even do better than that, though, couldn't they? Could you do better than 10,000 nines? A million? Oh, man, now Anna's embarrassed because that's way more than 10,000. Carter, you want another shot? 5 quadrillion. Is that even a number? I don't even know. What do you got?
1 bajillion.
1 bajillion. That's got to be the most, right?
2 bajillion.
But couldn't somebody do a bajillion and then another one? You see where I'm going with this? How close could you really get to 3.5? There's not really a good answer to that question, is there? Because couldn't you just keep getting closer and closer and closer? You just keep adding nines onto the end of 3.4, 9, 9, 9, 9. You just keep adding 9 after 9 after 9, and you would get a new y value. And then while you're figuring out that y value, Zach added another 9 onto the end. He came up with an even better y value than you, right? So, what does this all mean? Doesn't it mean essentially that I can't get to x equals 3.5? I can get really close. How close? Well, we could always just one-up each other for the rest of our lives, or we could just acknowledge that we can't actually get there. That make sense? So I would say that the answer to this one is there is no minimum. There's no minimum. We know where we want it to be. We want it to be right there at 3.5, at x equals 3.5. We want it to be right there. But the truth is that graph doesn't exist there. And that would be the low point if the graph did exist there. But the fact is the graph doesn't exist there. So there is no minimum. What do you think about the maximum now? There's no max. There is no maximum. Because as much as we want the max to be at y equals 4, how close could you get to that point? Well, we could start the whole process all over again, couldn't we? And say, well, I got closer than you, and then Kaylin got closer than both of us, and then Shirley came in with 1,000,000 nines, and then, Hunter had a bajillion, right? You can get closer and closer, but you can never actually get there, so there would be no max. There would be no min on that one. Maybe that helps you with upper right. When we come back here, what do you guys think the max or the min is for that upper right? Come on, don't just sit there.
Aren't any...
I disagree.
There's no max, but the minimum is like negative 1.25.
No, so I agree that there is no maximum, because what would have been the highest point, the graph doesn't exist there, doesn't it? But I think the minimum does exist, but Zach, I disagree with your number.
Is that negative 2?
Wouldn't it be over here? Isn't that the lowest point?
Yeah.
So I would say the minimum is negative 2. I think you must have been looking at this low point. That's definitely a low point, but there are points over there to the left that are lower than that.
What would you call that, like a local minimum?
We call it a local min or a relative min. Yep, and we will come around to that eventually. Okay, so this is getting at a couple of really good ideas here. So flip over to the next page and check out these questions. So based on what we just did, what condition do you think must be in place in order for our graph to have a maximum and a minimum? Didn't totally catch that. Say again?
The point must exist.
Okay, the point must exist. Think bigger ideas.
Like it must be continuous.
Oh, there it is. The graph must be continuous to guarantee that you have a max or a minimum. So this has a name, this thought. This is called the extreme value theorem abbreviated EVT. So we have an IVT, we have an MVT, and this is the last of the VTs. This is called the EVT. And this is an existence theorem again. And this basically says if F is continuous on an interval like A to B, then F has a max and min on that interval. Okay, so the condition there is continuity. And if we do have a continuous graph, unlike a couple of the ones we just had, if we do have a continuous graph, then we know for certain we will have a maximum value somewhere in there, and we will have a minimum value somewhere in there. It's called the extreme value theorem. Okay. So based on what we just did on that other page, when we found, looks like maybe Zach has a question, or no? Yes?
What is that interval you wrote?
Oh, goodness. Sometimes I do silly things. This should be an X. If X is between A and B, and the graph of F is continuous on that interval, then you'll have a max and you'll have a min. So notice this doesn't tell us what the max is and what the min is. It just says you'll have one of each. The condition is continuity. Fair enough? Okay. So based on what we did with those graphs a second ago, where do you think these maximums and minimums would happen? These maxes and mins on these intervals, there's candidates. And I don't use that word flippantly. It's almost like, think of it like this. It's almost like, we got the presidential election coming up next year. And some of you will be eligible to vote, right? 18 to vote? Yeah. So I don't know who the Democratic nominee is. I'm presuming the Republican will be Donald Trump. And let's say you're like, I don't really like Donald Trump very much. And you know what? Frankly, I don't like the Democratic nominee either. You know who I'm going to vote for? I'm going to write in a candidate, Mr. Anderson, my math teacher from last year. So you could do that. Did you know that? You could write me in and say, well, I don't know Donald Trump very well, but what I've heard I don't like. The Democratic person, I don't really like them either, but I know Mr. Anderson, and I like that guy. I'm going to write his name in. Do I have a chance of winning?
No,
Why?
not enough people know.
Yeah, I'm not really a realistic candidate, am I? It's just not a realistic possibility. So as much as I would appreciate the sentiment there, I would say, gosh, you're sort of wasting your vote. I mean, it's a cool statement and everything, but you're sort of wasting your vote, right? Not going to win. I'm not even trying to win. And, I would hate for the media to start digging in my past. Like, what did he say to that one girl when he was in 6th grade? That was really mean. And what did he cheat on that test when he was in 4th grade? Maybe he did. Yeah, I would hate that, right? I'm not even a realistic candidate. It would be sort of a pointless thing. So my question here is, what are the candidates that you should even think about? What would be the realistic candidates for a max or a min? Did you pick up on this on those graphs? If you have to flip back to those graphs. Where do you think the realistic candidates would come from? Say again?
Ones without holes in the graph.
Okay, ones without holes, yes. So we have to establish that the graph is continuous. And so once we've established that the graph is continuous, now we dig deeper and we say, okay, we've got a continuous graph, so we know there's going to be a max, we know there's going to be a min. Well, then on that graph, where would the realistic candidates come from? What do you think, Luke?
Well, I was just wondering, so it has to be continuous, but it doesn't have to be differentiable.
Correct. Correct. Jed, what do you think? Or was that your question?
No, I was thinking like inflection points.
Inflection points. Okay, so I'm not going to go back. A couple of these graphs had inflection points. Like the lower two had inflection points. Like I would say that the lower two had inflection points at x equals 1, x equals 2, x equals 3, and maybe x equals 4. Do those look like places where that graph has a max or a min? So he's starting to dig in the right kind of places, though. Inflection points isn't what I'm looking for, but he's starting to dig in the right place. Come on. What would our candidates be? What do you think, Cole?
Where the slope is 0.
Ooh, oh, now we're talking. Where the slope is 0. So I've got this other graph here. Would you guys agree with me that on this graph, the slope is 0 there, and the slope is 0 there? Do you see how those might be the high or the low points? We're going to come back around to that. So I'm going to say when slope of graph equals 0. That's what Cole said, and that's a really good point. But you can even see on my blue graph up here that I'm using, you can see that one of those places where the slope of that graph is 0, that actually is the max, isn't it? But the other one's not the min. So what would be the other category of candidates that would work here? The end of the interval? Was that what you were going to say? Yeah. I'm going to call that classification endpoints. Endpoints. So the left endpoint, the right endpoint, those could be the high or the low. So we're really boiling down our candidates to a pretty small list, kind of like Republicans and Democrats. You could always vote for the Green Party person or the other ones that nobody's ever heard of. If you do, good for you. Probably wasting your vote, but we can debate about the politics of that some other time. My point is, these are your realistic candidates right here. I'm going to leave this one as is. This is, well said, the end of the intervals, the endpoints. That's what I'm going to go with there. Slope of graph is 0. I'm going to add a little bit to this. I'm going to say where the slope of the graph is 0 or undefined. And that would be if the slope is undefined. Now we're talking possibly about a sharp point, right? And if the graph is continuous, but not differentiable, we are talking about a sharp point, right? Okay, so where the slope of the graph is 0 or is undefined, I'm going to go back and I'm going to call this graph f of x. And I'm going to rephrase that, and I'm going to say where f prime equals 0 or f prime doesn't exist. Those would be our two classifications of candidates, okay? So if I'm looking for a max or a min, I need to think about two sets of candidates. I'm looking for where f prime is 0 or doesn't exist, as well as I got to consider endpoints. That's where the max and min will happen. It's unavoidable. It's got to happen there. Max and min won't happen at all if we don't have a continuous graph, but if we do, those are your candidates. Okay, how are we doing? Hope this has been helpful. I'm gonna give you a more formal presentation, and then we'll do one example, and then we'll be done. And by the way, as far as thinking way out in the future, as far as final exam, we are headed towards kind of the terminal point for the first semester here. Our last topic is optimization, which is finding maximums and minimums. So we'll keep going a little bit afterwards, but as far as final exam material, this is it. We're going to explore this for a while, and then this will be it for our first semester final. Okay, so the extreme value theorem, let's see if we can fill in some blanks here based on what we've been talking about. If f is blank on the closed interval, continuous, that's our lone condition. Well said. So if f is continuous on the closed interval a to b, then f has both a minimum and a maximum on a to b. Some terminology here. Extrema on a closed interval can also be called absolute maximums and minimums, or, Luke, this will kind of go along with what you said earlier, global as opposed to local, right? So extreme on a closed interval, you could call them absolute maxes and mins or global maxes and mins. So you'll see those terms just used interchangeably on WebAssign, AP tests, stuff I might say. I say absolute a lot, but sometimes global. Okay, so here are your candidates. This is what we just were talking about. So candidates, absolute extrema, will happen at one of the endpoints, either one of them, or at what we call a critical point or critical number. And then down below, we'll see the definition of what a critical number is. We would say that C is a critical number if f prime of c equals 0 or does not exist. Are we tying this together okay with what you guys were playing with earlier? I hope we are. Here's one more connection. Back to Unit 3. And this, it's really right what Cole said. If f prime of c equals 0, then the graph of f of x has a blank, blank, blank at x equals c. Do you know what it would be? Say again?
Horizontal, like tangent line.
There it is, horizontal tangent line. Well said. So horizontal tangent line, and you've seen this on examples and practices and quizzes and a test at least once, maybe twice. So I just wanted to connect it back there. So you can see, of course, here you've got a horizontal tangent line there, horizontal tangent line there. There's an endpoint, there's an endpoint. That would constitute, for that graph at least, all of your candidates. If you think about it like this, if you couldn't boil it down to your candidates and you didn't have a graph, you would never get this done. Because could you possibly test out all the points on the interval? You could try, but you'd never do them all, right? And so if you could boil it down to these are my 4 candidates, or these are my 3 candidates, or my 5 candidates, it's actually a pretty easy process to decide where the max and min would be. Okay, I think it's time for an example. I can tell you're ready. Let's do. Here we go. I want to kind of do this one with you a little bit. I want to get some back and forth here. Let's read through what it says. Find the absolute or global maximum and minimum of f of x on the interval -1 to 3. And I would say, I think for the most part, this would be a no calculator question. And by the way, even if the calculator were active, on a question like this, if you were to say, hey, I used my calculator and I graphed it and I used the max min finder like I did in pre-calc and algebra 2, and the max is this, it's never going to fly. Like if your reasoning is, hey, look at my calculator, you won't get credit for that. Okay? I want to see that there's some deeper analysis beyond, I have eyes, they work, and I looked at my calculator. Anyways, here we go. What are the candidates for absolute maximums and minimums? So that was said so quietly, or my hearing is so bad, I heard you say something.
On the interval of -1, 2, 3.
Yep. So what are my candidates, though? Like, what should I test out?
-1, or where f of x equals, actually never mind, f of -1, f of f prime equals 0.
Okay, so Cole has said it quite well. I'm going to say it in a slightly different way. He said, I want to test out f of -1 and f of 3. And he said also where f prime is 0. So let's go back. Let's think of the categories here. My candidates come from endpoints and, I can tell we need to do this a lot. We're going to say it a little more succinctly. We're going to say endpoints and critical points. Candidates are endpoints, which Cole mentioned, -1 and 3. So that's correct. And critical points. Critical points are places where what is happening?
Slope is where f prime is 0 or undefined.
There we go. So if we're trying to figure out where f prime is 0 or undefined, I better figure out what f prime is first, right? So here we go. F prime equals, well, we got a couple of power rules here. Hoping that that's going well for you. This is what I'm coming up with for f prime. You guys get the same thing? Okay. So let's remember what Zach said. We're looking for places where f prime is 0 or doesn't exist. So I always will try to deal with the doesn't exist first, because often that's the harder thing to think about, and I'd rather get that out of the way. Can you guys think of any values where f prime just wouldn't exist? Sometimes the answer is going to be, no, there are no values. F prime exists for all x values. Sometimes there's going to be, yeah, There's a place where f prime doesn't exist. So take this question for what it's worth. It's a real question. Can you guys see any places where f prime doesn't exist? One? Why?
Because 1 to any power is 1 times 2. I guess that'd be 0.
You've actually discovered another important point. Let me rewrite this. Maybe you'll see something a little bit different. Would you guys agree that this is equal to this? Isn't x to the negative 1/3 really a denominator? Now, do you see any places where f prime doesn't exist? At 0, at x equals 0. Why? You can't divide by 0. You still can't. Even though you're in calculus, you still can't divide by 0. So I would say f prime does not exist at x equals 0. That means 0. Am I off on my times? Did we go to 55?
I think it's 50.
Is it really 50? Well, let's finish this thought here. Okay, so that means one of my candidates is 0. This finishes fast. I also have to consider f prime equaling 0. So this becomes equation that I need to solve. What would you guys do to solve this? Oh, you guys are so quiet this morning. Okay, so I would add 2x to the negative 1/3 to both sides. Then I would divide by 2. And then how do I get the x fully by itself?
Drop it down.
Oh, it's negative 1/3. There we go. Sure, you could drop it down. So it'd be this.
Multiply x over that.
Okay. How do I solve this now? Cube it. Whoever said that? Yeah, cube both sides. So cube this side, cube that side. And this is actually what Zach came up with a while ago. X equals 1 causes f prime to not exist. That is my fourth and final candidate. Okay? So how do I decide what the max and the min are? I'm going to take these candidates and I'm going to plug them back into my original function. Figure out where y is highest. So a couple of these are super easy. What if I plug in a 0? What's the output?
0.
Yep. What if I plug in a 1? What's the output? Negative 1. The negative 1 actually pretty straightforward. 2. This would be what? Negative 2 minus 3, I think?
Comes out to 1. Negative 1.
Plug in a negative 1. Equals negative 2 minus 3 times negative 1 to the 2/3.
So it might just be negative 1.
No. Negative 1 2/3 would be 1. So f of negative 1 would be negative 2 minus 3. So I'm getting negative 5 there. The only one we might need to use a calculator is the 3, right? Would you guys use your calculator really quick? Is it really? Is it really that time? I can never remember. Oh, that's what it is. It says 55 on there. Hey, did anybody figure out the 3? This will just take 1 second. Come on.
Negative 0.24.
Negative 0. Let's do 3 decimals. We never do 2 decimals. We'll call it 238. Yes? No? Oh, it is literally 240. Okay, cool. Okay, so, sorry, you can look at my calendar out there. It says till 55, but it's a typo. What's the max? 0. What's the min? We're done. Make sense? Fantastic. Sorry to keep you late. My schedule is off out there. Hey, we'll keep practicing this tomorrow.
So to finish, it would be just right now 0, min, negative 5.
Right there.
And then you get all your points.
Sir, thank you guys. Have a great day.